Welcome back, everyone. Today is going to be my first ever video on organic chemistry. I'm still learning how to use technology, so I am holding the microphone. Today we're going to be talking about resonance.
Resonance.
I hope the semester is going well for you so far, and I hope this video helps you out. In this video, we're going to be talking about what resonance actually means, its application in real life, what those plus and minus charges actually are, as well as some problem-solving strategies. So we're going to be giving you a few examples on resonance structures to give you tips on how to figure out how many there are and how to draw them. If you don't know what that means right now, that's okay. We're going to go over that in a second. So what is resonance really? Resonance structures are simply a way to describe the movement of electrons in a given compound. This is because there are different ways a compound can bond through its electrons. Later on, we'll talk about resonance hybrids, which is basically just an average of all of the resonance structures. Resonance in real-life applications is able to stabilize compounds. So when resonance is present in a compound, it's actually more stable than structures that do not have resonance. Some forms are more likely to form than others, and we'll get back to this when we talk about major and minor contributors. And resonance can also alter the chemical properties like boiling point, melting point. It can also affect its planarity. For example, if a double bond forms, it becomes planar. Okay, so that's 2 of the 4 topics already down. So now we're going to briefly talk about what the positive and negative charges mean. When something is positive, it means that it's missing electrons. And then when something's negative, it means there are extra electrons. So, for example, in this case, oxygen has a negative charge because it typically wants to form 2 bonds and have 2 lone pairs, but in this case, it has 3 lone pairs and only 1 bond. Okay, that's 3 down. Now we're going to take a brief detour to talk about sigma bonds, pi bonds, and the resonance hybrid structures. If you recall, sigma bonds are the single bonds between 2 atoms. Pi bonds are any bond after that. So another way of saying that is that the first bond in a double or triple bond is always still a sigma bond, but all the bonds after that are pi bonds. So when there's a double bond, there's 1 sigma bond and 1 pi bond. And when there's a triple bond, there's 1 sigma bond and 2 pi bonds. So you can think of resonance hybrids as an average of all of the resonance structures. You draw that double arrow when you're drawing a new resonance structure between the 2. So here I'm just drawing a benzene ring, and those pi bonds are moving about the ring. So the hybrid structure of that can be drawn showing the dotted lines, or in the case for benzene, you could also draw a circle, and those show that those electrons are moving in that path. Another way to think about resonance structure hybrids is through this example of the Liger. If you are a geneticist, I am so sorry you have to hear this example, but it's something that helped me learn what resonance hybrids were. So let's say a tiger and a lion make a baby. It's going to be a Liger. I was not going to try drawing that though. The baby is a combination of the tiger and the lion. It's going to be a hybrid of the 2. It's not going to be 50% this and 50% that. It's going to be a combination, and both of the traits are going to be presented at the same time. That is how you can think of resonance structure hybrids. The resonance hybrids are an average or a combination of the resonance structures. So now we're going to just go into some quick problem-solving strategies that helped me when I was learning resonance structures. The biggest one I would say is make sure you're drawing new structures 1 step at a time. What that means is try not to draw too many arrows, pushing mechanisms, and steps moving around, and just keep it simple. So you take 1 step, you draw a new resonance structure, take another step, draw another resonance structure. This helps prevent you from missing resonance structures. It's especially important in exams where it's like draw all of the resonance structures of this molecule. What I do when I'm solving problems is I will draw the original backbone of the compound, so the things that will not change between structures, and then afterwards I typically use a new color. to draw in the new stuff. Another thing to note is when you're drawing resonance structures, the formal charge must stay the same between them. So if you start off with a neutral compound, it has to either stay completely neutral or the charges have to add up to be a formal charge of 0. Okay, now we're going to move on to some examples. So this one's a negative charge example. Those negatives are the extra lone pair on the oxygen is going to want to move down and form a double bond with the ring. So since that carbon that's connecting the oxygen to the ring is going to have 5 bonds at that point, which cannot happen, the pi bond is going to have to move those electrons to the next carbon. That carbon is then going to have a negative charge, which carbons do not like to have. So it's going to try forming a pi bond, and then the negatives are going to have to move over to the next carbon, and so on and so forth. And this is going to happen until it reaches the oxygen again, in which case that double bond is going to be forced to move up to the oxygen, and it's going to form that original structure we were given. So in this case, there are 4 total resonance structures for that given compound. Our second example is going to be a neutral atom. So I drew in those lone pairs there because oxygen in this case has 2 lone pairs, 2 bonds, neutral. If that bond decided to move up to the oxygen is going to have a negative charge. And since those electrons left that carbon, it has 1 less bond, and the carbon's going to have a positive. So if you recall from before, we were talking about how the formal charge has to maintain the same thing throughout all of the resonance structures. The first one's neutral. The second one, that still has a formal charge of 0 because +1 and -1, those 2 charges. Then we could say the pi bond could move over to essentially fix that positive charge in that place, but then the positive charge is going to move to the other side of that compound. It's important to note, so carbocations are when the carbons have a positive charge and carbanions are when they have a negative charge. Due to electron density, the tertiary form of a carbocation is going to be the most stable. So that second resonance structure that we drew, where the positive charge is on the carbon that has 3 bonds connected to it. And when I say 3 bonds, I'm saying 3 bonds that are not including hydrogen. And that makes it tertiary. It's going to be the most stable in that sense. Primary is going to be the least stable. For carbons that have negative charges, the primary form is going to be the most stable. And it's going to be more likely to form. So this plays a role when you're going into the major and minor contributors, which we'll get to right now. So let's say you have a substance that has multiple resonance structures possible. The major contributor makes up most of that percentage. Major contributors are the ones that have the least amount of charges. So that would be this first one that we were given here. And the minor ones are going to be the ones with charges or the ones that are least stable. So between the second 2 that we drew in, the top one is going to be more stable than the bottom one, because if you remember, we just talked about how for carbocations, it's most stable in its tertiary form. When drawing resonance structures, make sure you have an actual arrow. If you only draw one line coming off of the arrow and you have like half an arrow, that means that only a single electron is moving. So in all of these pushing arrow mechanisms, there are 2 electrons moving at a given time. Okay, great work everyone. That's going to conclude the video for today. I hope you have a great rest of your day and good luck in the upcoming semester. Thank you.